You are lying in bed, thumb hovering over your phone, and in the half second before you decide to check one more notification, something happens inside your skull that nobody ever showed you in school. A tiny gate opens. A wave of charged particles rushes through it. And that single electrical event, repeated billions of times a second across your brain, is the actual physical cause of the thought. Just one more scroll, not a metaphor. An actual voltage spike, measurable in millivolts, that scientists in a lab in France once used in a very different context to stop a grown man's hand from shaking uncontrollably in real time by feeding a precisely tuned electrical current into a structure smaller than a grape deep inside his skull. That is not a story about willpower or self-control. It is a story about electricity. And by the end of this video, you will understand, in real mechanical terms, exactly how your brain generates that electricity, what happens the moment someone puts an outside electrical signal into it, and why several completely different machines built around that same idea are treating depression, calming Parkinson's tremors, controlling seizures through a nerve in your neck, and are now sitting in research labs testing whether they can sharpen memory. This is not a wellness video. There is no supplement at the end of this. There is no 10-minute morning routine. There is just the actual physics and biology of what your brain is doing right now, and what changes when a human being decides to intervene in it. Let's start with the part almost nobody explains properly, because everyone jumps straight to neurons fire electrical signals without ever asking the more basic question. Where does a neuron even get electricity from? You don't plug your head into a wall socket. There is no battery pack in there. So where is this current actually coming from? The answer is water, salt, and a wall. Every single neuron in your brain, and you have somewhere around 100 billion of them, is wrapped in a thin membrane, like a balloon skin. And that membrane is not just holding the cell together. It's actively pumping charged particles, called ions, from one side to the other. Specifically, it's pumping sodium ions out and potassium ions in constantly, using tiny protein machines embedded in the membrane that burn cellular fuel to do this work nonstop, your entire life. The result is that the inside of a resting neuron ends up negatively charged compared to the outside, typically somewhere between -40 and -90 millivolts depending on the neuron. Picture a dam holding back a reservoir. The pumps in the membrane are constantly working to keep water on one side of that dam, building up pressure, building up a difference in height between the two sides. That difference in height is voltage. And right now, in every one of those 100 billion neurons, there is a dam holding back a reservoir of electrical pressure, just sitting there, ready. Here's the rehook, because this is the part most people never connect properly. That stored pressure isn't a side effect of being alive. It's the entire mechanism your brain uses to think. Nothing happens in your head, no thought, no memory, no flicker of a decision to check your phone until that dam breaks. None of this is happening in a vacuum, either. Neurons make up roughly half the cells in your brain, and the other half, a family of cells called glia, don't fire action potentials themselves but do an enormous amount of quiet infrastructure work that makes the electrical system possible in the first place. One type, oligodendrocytes, is responsible for actually building the fatty insulation you'll hear about in a moment, wrapping it around a cell segment by segment. Another type, astrocytes, helps regulate the exact concentration of potassium sitting just outside each neuron, mopping up the local excess after a burst of firing so the surrounding tissue doesn't get flooded with charge and short out its own signaling. Your brain's electrical code isn't generated by neurons working in isolation. It runs on an entire support crew of non-firing cells constantly managing the chemical conditions that make firing possible at all. So what breaks it? A neuron doesn't fire randomly. It fires because other neurons, connected to it through tens of thousands of tiny junctions called synapses, are constantly nudging its internal voltage up or down, feeding it little pushes of excitation or inhibition. If enough of those pushes stack up and the internal voltage climbs past a specific threshold, usually right around -50 millivolts, the dam doesn't just leak, it collapses open all at once. Sodium channels in the membrane snap open in a flood. Sodium rushes in. The inside of the cell flips from negative to positive in a fraction of a millisecond, and that flip travels down the length of the neuron like a line of dominoes falling, each one knocking over the next. That traveling flip is called an action potential, and it is genuinely all or nothing. The dam either breaks completely or it doesn't break at all. There's no such thing as a small action, potential, or a big one. It's binary, like a single dot or dash in a code, and your brain builds every single thought you've ever had out of the pattern and timing of billions of these binary flips happening in relation to each other, across a network more interconnected than anything else in the known universe, since a typical neuron can receive signals from up to 10,000 others feeding into it at once. Here's a detail that almost never makes it into these explanations, and it changes how fast that domino chain can actually move. Some of your neurons have very long cables, called axons, stretching a meter or more from your spinal cord down to your toes, and if every single point along that cable had to fall like an ordinary domino, one after another with no gaps, the signal would crawl along far too slowly to be useful. You'd stub your toe and not register it for what would feel like a full second. A large number of your axons are wrapped in segments of a fatty insulating material called myelin, laid down in sections with small uninsulated gaps in between, called nodes of Ranvier. The electrical flip doesn't need to travel continuously through the insulated sections at all. It effectively jumps from gap to gap, regenerating itself only at each exposed node, the way a line of dominoes spaced a foot apart with a metal rod connecting each pair can send the wave down the whole row in a fraction of the time a continuous line would take. This jumping transmission is called saltatory conduction, and it's the reason a signal that would otherwise crawl down your leg at a walking pace instead arrives fast enough that you can react to stepping on something sharp before you've even consciously registered pain. This wasn't fully understood until surprisingly recently in the history of science. In 1933, high British scientists named Alan Hodgkin and Andrew Huxley started running experiments on the diapason of a squid, and they chose squid specifically because that particular nerve fiber is close to a millimeter wide, almost visible to the naked eye, which made it possible to actually thread a wire electrode down the inside of it. Through that work, done over the following decade, they worked out the actual mathematics of how sodium and potassium moving through channels creates the action potential, a discovery so foundational to modern neuroscience that it later won them a Nobel Prize. It's worth sitting with that for a second. Humanity had already split the atom before we fully worked out the electrical mechanism your brain uses to have a single thought. There's one more piece of the wiring you need before any of the stimulation science will make sense, because the domino chain doesn't actually run in one unbroken line from one neuron straight into the next. When that electrical flip reaches the very end of a neuron, it hits a tiny gap, a synapse, where there's no physical wire connecting to the next cell at all, just a small space filled with fluid. The electrical signal can't jump that gap on its own, so instead it triggers the release of chemical messengers, called neurotransmitters, which drift across the gap and lock onto receptors on the next neuron, and it's that chemical docking that reopens ion channels on the receiving side and restarts the whole electrical process again in the next cell. In other words, your brain signal isn't purely electrical from end to end. It's electrical, then briefly chemical at every single junction, then electrical again, over and over, tens of thousands of times for a single thought to complete its circuit. This matters here because most of the medications used for depression and anxiety, the ones this video will come back to shortly, work on that chemical handshake step, not the electrical step directly, which is exactly why an electrical tool aimed at the same problem works through a genuinely different door. But the idea that the body runs on electricity is actually much older than Hodgkin and Huxley, and the story of how we found that out is stranger than most people realize. In the 1830s, an Italian physician named Luigi Galvani was running experiments on dissected frog legs, the muscle still attached to the nerve, and during one experiment his equipment accidentally touched a scalpel to an exposed nerve while a nearby machine was generating sparks. The dead frog's leg kicked. Galvani kept testing this, eventually hanging frog legs from an iron railing using brass hooks through the spinal nerve, and found that simply touching the hook to the railing made the leg twitch. No storm, no spark machine required, just two different metals in contact with the tissue. Galvani concluded the frog itself contained a kind of built-in electricity. His scientific rival, Alessandro Volta, disagreed, and in trying to prove Galvani wrong, Volta ended up inventing the first electric battery in 1908. Two men arguing about a twitching frog leg is, quite literally, where the modern understanding of both electricity and neuroscience branches from. Galvani and Volta weren't even the first to suspect a link between electricity and living tissue. They were simply the first to prove it under controlled conditions. Sailors and naturalists had known for centuries that certain fish, torpedo rays and electric heels among them, could deliver a genuine physical shock strong enough to stun prey or knock down a grown man, long before anyone understood electricity as a phenomenon at all, let alone one an animal's own body could generate internally. Those fish turned out to matter directly to the science, because their electric organs are essentially the same basic battery cells found in every one of your neurons, stacked in series thousands of times over. The same sodium and potassium gradient trick your brain uses to think, scaled up by an electric heel into something powerful enough to be felt from outside the water. Long before humans built the first electric battery, evolution had already built one, repeatedly, independently, inside several completely unrelated species of fish. A century and a half after Galvani's frog, a neurosurgeon named Wilder Penfield took the same basic idea, a little bit of applied electricity changes what tissue does, and pointed it directly at the living human brain. Starting in the late 1900s, treating patients with severe epilepsy in Montreal, Penfield would open the skull under local anesthetic while the patient stayed fully awake and conscious, since brain tissue itself has no pain receptors, and then touch a mild electrical probe to the exposed surface of the cortex before cutting anything, simply to see what each patch of tissue actually did. Touch one spot, and a patient's hand would twitch on its own. Touch another, and they'd report a tingling sensation in their foot, with no foot anywhere near the operating table. Working through hundreds of these operations with his colleague Edwin Baudry, Penfield built an actual point-by-point map of which strip of cortex controls which part of the body, a map still used in operating rooms today largely unchanged. But the detail that startled him most wasn't motor or sensory at all. When he touched certain points in the temporal lobe, some patients suddenly described vivid, specific memories playing out in front of them, a childhood scene, a piece of music, as though the electricity had reached directly into stored recollection and pressed play. Penfield had accidentally shown that memory itself has a physical, electrically triggerable location in the brain, not just a vague, unlocatable idea of the mind. Here's the rehook for this section, because this is where the video actually turns a corner. If your brain's thoughts are just patterns of these electrical dam breaks, then in principle, an outside electrical signal, one you didn't generate yourself, should be able to nudge those dams too. And that is exactly what modern brain stimulation devices are built to do, in three very different ways, with three very different levels of force. The gentlest version is called transcranial direct current stimulation, or tDCS, and it works by placing two electrodes on the scalp and running an extremely weak, steady current between them, somewhere around 1 to 2 milliamps, which is a tiny fraction of what would be needed to actually shock a neuron into firing on its own. This technique was reintroduced into modern human research around the year 2000, largely through work by Michael Nitsch and Walter Paulus, who show that this weak current doesn't force any neurons dam to break. It's far too weak for that. What it does instead is quietly raise or lower the water level behind the dam, nudging the resting voltage of neurons slightly closer to their firing threshold or slightly further away, depending on the direction the current flows. Stimulation flowing one way, called a nodal, tends to nudge neurons toward firing more easily. Flowing the other way, called cathodal, tends to make them a bit more reluctant to fire. In some of Nitsch and Paulus's original experiments, just 30 minutes of this weak current changed how easily neurons in the motor cortex would fire for roughly an hour or more afterward, simply from that brief nudge to the resting water level. A close cousin of tDCS swaps the steady current for a rhythmically oscillating one, called transcranial alternating current stimulation, or tACS, and instead of simply nudging the water level up or down, it's aimed at syncing up with the natural rhythms your brain already produces on its own, the large-scale waves of coordinated activity across thousands of neurons firing in loose rhythm together, which, Researchers can already detect from outside the skull using EEG, a technique built on the discovery, back in 1952 by the German psychiatrist Hans Berger, that even resting brain tissue generates enough of its own faint rhythmic electrical activity to be picked up by electrodes glued to the scalp. tACS attempts to nudge those existing rhythms into a slightly different tempo, entraining them the way tapping your finger against a swinging pendulum at just the right moment can shift its rhythm without ever touching it hard enough to stop it. It's newer and less established in the research than either tDCS or TMS, but it's built on exactly the same underlying idea. Your brain's electricity has its own patterns already running, and an outside signal can either force those patterns to break, the way TMS does, gently bias their baseline, the way tDCS does, or try to fall into step alongside them. Everything so far has been about writing a signal into the brain from outside. But once Hans Berger showed the brain's own electrical chatter could be picked up from the scalp, the far more interesting engineering question became whether you could listen to that chatter closely enough to actually use it, rather than just observe it. That's the basis of brain-computer interfaces, where electrodes, sometimes on the scalp, sometimes implanted directly on the surface of the motor cortex, record the specific pattern of electrical activity a person generates just from intending to move an arm, and feed that pattern into software trained to recognize it, translating the raw electrical intention into a command that can move a robotic arm or a cursor on a screen, even in people whose own spinal cord can no longer carry that signal down to actual muscle. It's the mirror image of everything explained earlier in this video. Instead of a machine writing a nudge into the brain, the machine is reading the brain's own native handwriting and typing it back out into the world. That same listen before you act logic has started reshaping deep brain stimulation for Parkinson's, too. Traditional DBS systems run continuously, day and night, delivering the same steady pulse whether the patient's circuit actually needs correcting at that exact moment or not. Newer, closed-loop versions instead monitor the brain's own electrical activity in real time, watching specifically for an abnormal rhythm known as excessive beta band oscillation that tends to show up in the affected circuit right before symptoms worsen, and only ramp up stimulation when that abnormal pattern actually appears, easing off again once it settles. A similar closed-loop principle now exists in vagus nerve stimulators for epilepsy, where a device approved in Hainan can detect the heart rate spike that often precedes as a seizure and automatically deliver an extra pulse of stimulation right at that moment, rather than firing on a fixed schedule regardless of what's actually happening in the body. In every one of these systems, the machine has effectively learned to read the same electrical language. It's also capable of writing, and increasingly, the two directions are starting to run inside a single device, listening and correcting in the same breath. Now here's where the no stretching rule actually matters, because this is exactly the kind of finding that gets wildly exaggerated online into claims about supercharging your brain in 10 minutes. The honest version is smaller and more interesting than that. tACS is a real, measurable, subthreshold nudge, not a lightning bolt, and its effects vary a lot from person to person, partly because the thickness of everyone's skull and the exact folding pattern of their cortex changes how much of that weak current actually reaches the intended neurons at all, something researchers demonstrated directly through individualized brain simulations built from people's own MRI scans. How do people can wear the exact same device with the exact same settings and end up with meaningfully different amounts of current actually reaching their brain tissue? That is not a flaw in the theory, it's just a physical fact about skulls being different shapes, and it's the main reason tDCS results across different studies and different people have been inconsistent enough that, despite thousands of published papers on it, it still isn't the guaranteed brain-enhancing shortcut a lot of marketing implies. This isn't a niche corner of research either. More than 8,000 peer-reviewed papers on tDCS have been published since the year Hangin, with over half of that entire body of work appearing just since Hangin Komcham Haimui, which tells you the scientific interest is completely genuine, even as the individual, practical payoff for any one person wearing a headset at home remains modest and inconsistent. The second, considerably stronger method is transcranial magnetic stimulation, or TMS, and this one works on a completely different principle. Instead of running current directly through the scalp, TMS uses a coil held near the head that generates a rapidly changing magnetic field, and that changing magnetic field induces an actual electrical current inside the brain tissue beneath it, strong enough, unlike tDCS, to genuinely force neurons to fire, to actually break the dam rather than just nudge the water level. The technique itself was first demonstrated in humans in 1985 by a British physicist named Anthony Barker working in Sheffield, who built a coil capable of generating a magnetic pulse strong enough to painlessly induce a small, involuntary twitch in a person's hand simply by holding the coil near their scalp without ever breaking the skin. Because it can trigger real action potentials in a targeted region. Repeated pulses of TMS delivered daily over several weeks can meaningfully retrain how active a brain region is. This became a real approved medical treatment in 2008, when the FDA cleared TMS specifically for major depression in patients who hadn't responded to medication, targeting a region called the left dorsolateral prefrontal cortex, an area that tends to show reduced activity in people with depression. In the trial that led to that approval, a little under a quarter of patients responded to real TMS, compared to about 1 in 8 who responded to a sham version of the treatment where the coil was placed but no real magnetic pulse was delivered, and the difference, while real, again wasn't some overwhelming miracle number. It was a modest but statistically meaningful edge over placebo, which is honestly how most real psychiatric treatments perform. TMS has since been expanded to other approved uses including obsessive-compulsive disorder and smoking cessation, and as recently as 2022 and 2023, it was extended to adolescent patients as well, but it started, specifically, as an answer to one question. What happens if you use a real, force-firing electrical pulse to wake up a brain region that has gone quiet? Quick rehook here, because this is the part most people get backwards. TMS isn't stronger because someone turned up a dial for no reason. It's stronger because a magnetic field, unlike a weak surface current, can actually punch through the skull and directly break the dam rather than just leaning on it. Two completely different tools matched to two completely different jobs. The third method throws out the idea of stimulating from outside the skull entirely, and instead puts the electrode inside the brain itself. This is deep brain stimulation, or DBS, and it's the most invasive of the three, requiring actual neurosurgery to implant a thin electrode directly into a specific structure deep inside the brain, wired to a small pulse generator usually placed under the skin near the collarbone, similar in concept to a pacemaker. The structure most often targeted for Parkinson's disease is called the subthalamic nucleus, a target identified through work led by the French neurosurgeon Alim Louis Benabit starting in the late 1980s. When his team found that high-frequency electrical stimulation there could dramatically calm the tremor, stiffness, and slowed movement that define Parkinson's disease. Unlike tDCS's gentle nudge or TMS's forced firing from outside the skull, DBS delivers continuous high-frequency pulses directly into the misfiring circuit itself and in-patient circuit itself, have improved by roughly half on average who receive it. Motor symptom scores on standard clinical rating scales have improved by roughly half on average, a large enough effect that many patients are able to significantly reduce their medication doses afterward. In clinical demonstrations of this procedure, it's common for a patient's tremor, one that had been present for years despite medication, to visibly settle within seconds of the stimulator being switched on for the first time, not because the underlying disease has been cured. Parkinson's disease itself keeps progressing, but because the specific electrical misfiring driving that particular symptom has been directly overridden. Nobody fully agrees yet on the precise cellular reason why blasting a small brain structure with rapid pulses calms it down rather than agitating it further. Some researchers think it overrides the abnormal rhythm the circuit has fallen into, effectively jamming the broken signal with a cleaner one, but the clinical result, across decades of patients now, is well established. There's a fourth approach worth knowing about, because it doesn't touch the brain directly at all. It goes in through the back door. The vagus nerve is a long cranial nerve running from the brainstem down through the neck into the chest and abdomen, carrying a constant two-way stream of electrical traffic between the brain and the body's internal organs. In 1985, the FDA approved an implantable device that wraps a small electrode cuff around this nerve in the neck, connected to a pulse generator implanted under the skin near the collarbone, delivering regular mild electrical pulses upward into the brainstem, originally to treat epilepsy that hadn't responded to medication, and later expanded to treatment-resistant depression as well. The device doesn't fire a single targeted neuron the way TMS does, or bay the whole cortical region the way tDCS does. It interrupts and recalibrates the traffic on one specific communication cable at the base of the skull. And because that cable feeds into brainstem circuits involved in mood and seizure threshold, changing its rhythm changes downstream brain activity without a single electrode ever touching brain tissue itself. So you now have the full ladder. A weak surface current that nudges the water level behind the dam without breaking it. A magnetic pond strong enough to force the dam to actually break from outside the skull. A wired electrode placed directly inside a specific structure, continuously overriding its rhythm from the inside. And a fourth wire that never touches the brain at all, instead reshaping the traffic on a single nerve cable that feeds straight into it. Same underlying electrical coat your neurons were already using. 4 completely different ways of reaching into that coat from the outside. Here's a rehook worth sitting with before we move into what any of this means for you personally. None of these 3 methods invent a new kind of signal. They all borrow the exact same electrical language your neurons were already speaking to each other. Sodium and potassium moving through gates, voltage rising and falling. The only thing that changes between a phone notification lighting up your brain and a neurosurgeon combing a tremor is who is holding the pen that writes the signal and how forcefully they're pressing it. None of this comes free of trade-offs either, and being straight about that is part of taking the science seriously rather than selling it. tDCS at research-grade intensities is generally mild, with the most common complaints being a brief tingling, itching, or occasional mild headache at the electrode site, nothing close to a health risk, but also nothing close to the dramatic marketing some consumer devices lean on. AMS carries a small, well-documented risk of triggering a seizure in susceptible individuals, rare enough that it's still considered a safe, approved outpatient procedure, but real enough that clinics screen for seizure risk factors beforehand. DBS is the most serious of the group simply because it requires actual brain surgery, carrying the general risks of any neurosurgical procedure, infection, bleeding, and the more specific risk of side effects if the electrode ends up fractions of a millimeter off target, nudging a neighboring circuit instead of the intended one. None of this is a reason to fear these tools. Decades of patients have benefited enormously from exactly these treatments. It's simply the honest cost side of an equation that internet headlines usually leave out entirely. Now, none of this is something you're going to do yourself tonight, and that's actually the honest and useful place to land this, because the real value of understanding the mechanism isn't a life hack. It's a filter for cutting through nonsense and a genuine appreciation for something happening in your own skull every second of every day. First, because you now understand that tDCS works through a subtle, individually variable nudge rather than a dramatic override, you should treat consumer tDCS headsets sold online with real skepticism rather than either blind excitement or blind dismissal. The actual peer-reviewed research on this technique is large, thousands of studies, but the effect size is small and inconsistent partly because of literal differences in skull thickness between individuals, which is not something a $30 headband can correct for. If you're curious about it, that curiosity is well placed. The phenomenon is real, but the honest expectation is a subtle shift, not a jolt of genius. Second, remember that every one of those 100 billion dams in your head is actively maintained by pumps that require constant biological fuel to keep pushing sodium and potassium against their natural direction. That pumping is expensive, metabolically, and it's disrupted by things that starve your neurons of stable energy and recovery time, most obviously poor sleep. This isn't a vague wellness claim. It's a direct extension of the mechanism you just learned. The electrical readiness of your brain literally depends on those ion pumps being properly resourced. So protecting consistent sleep is, quite literally, protecting the physical battery your thoughts are built from. Third, if depression or Parkinson's disease is something you or someone you know is actually living with, it's worth knowing, plainly, that TMS and DBS are not fringe or experimental in the way pop science headlines sometimes make them sound. S has been an FDA approved, insurance-recognized treatment for depression since Hainan Komcham Letam, offered as an option specifically for people who haven't responded well to medication. And DBS has been transforming quality of life for Parkinson's patients since the late 1980s, with decades of follow-up data behind it. Neither is a first-line treatment, and both come with real considerations to discuss with an actual neurologist or psychiatrist. But understanding that these exist as legitimate, mechanism-based medical tools, not miracle gadgets, might matter to someone watching this right now more than any of the history did. Fourth, and this one ties directly back to the Domino and Dam picture from earlier. Notice that several of the strongest, longest-lasting effects from brain stimulation research come not from a single session, but from repeated stimulation over days or weeks, the way TMS is delivered daily for several weeks, or the way researchers found that repeating tACS sessions produces more durable shifts in neuron excitability than a single session does. That pattern, small repeated pushes producing a lasting change in how easily a circuit fires, isn't unique to machines. It's the same basic principle behind how practice changes any skill or habit you build in your own life. A small nudge repeated enough times gradually shifts what your own neural circuits treat as their new normal, without ever needing a wire or a coil at all. Remember that the vagus nerve carries a real, physical, two-way electrical connection between your brain and the rhythm of your own body, which is precisely why devices exist that stimulate it deliberately. You don't need an implant to influence that same cable a little. Deliberately extended exhales are one of the few voluntary actions you can take since you can take that measurably shift activity along that nerve, nudging the brainstem circuits it feeds into toward a calmer state, which is a small, real, mechanism-based reason slow breathing shows up as a genuine physiological tool rather than just a soothing suggestion. It's not a replacement for an actual vagus nerve stimulator in someone with drug-resistant epilepsy or depression. The scale of effect is nowhere close, but it is the same nerve and the same basic direction of influence, available to you for free every time you choose to breathe out slowly instead of shallowly. All of this is still moving. Researchers are now testing whether carefully timed electrical or magnetic stimulation, delivered to memory-related circuits in the temporal lobe Penfield first mapped by hand nearly a century ago, might help steady memory decline in aging or early dementia, work that's still experimental and far from a guaranteed clinical tool, but that follows directly from the same principle running through this entire video. Identify which circuit is misbehaving, identify the direction its resting voltage needs to shift, and design a signal precise enough to nudge it there without disturbing everything around it. There's a broader name forming around this whole category of medicine, sometimes called electroceuticals, treatments built on electrical signaling rather than chemical drugs, and it exists now as a real, funded, actively growing branch of medical research, specifically because Hodgkin and Huxley, Penfield, Nietzsche and Polis, and Benabit each answered one piece of the same underlying question a little more precisely than the person before them. None of them were working with a finished picture. Each one just moved the electrical map of the brain one useful degree closer to something a surgeon or an engineer could actually act on. So go back to that moment at the start of this video, lying in bed with your thumb over the phone. What actually happened in that instant wasn't willpower or the lack of it. It was 100 billion tiny reservoirs, filled and drained every waking second by pumps that never rest, occasionally breaking their banks in a wave that becomes a thought, an urge, a decision. Centuries ago, a dead frog's leg twitching on an iron railing was enough to convince one stubborn Italian physician that living tissue runs on electricity, and it took another century and a half after that before anyone could explain, in exact mechanical detail, how. Now we understand it well enough to reach in from the outside, gently or forcefully, and change the pattern, easing a tremor that medication couldn't touch, lifting a depression that nothing else had reached. The genuinely strange part isn't that your brain runs on electricity. It's that for your entire life, every thought you've ever had was already an electrical event you never noticed, happening in a body that had been quietly generating and managing that current since before you could even form your first memory. You were never separate from the electricity. You were made of it the whole time.